Hi everyone, a very good evening if you're watching it from India, and a very good afternoon if you're watching it from anywhere else in the world. And over here, I'm Shantanu. I'm the host and the creator of the Astro Geek comics, and this is Keeping Up with the Universe. And today with me, I have Kate. Hi, Kate. How are you?
Hi, I'm good, thanks. How are you?
I'm good, and thank you so much for joining our fourth episode. And for everyone who's watching it right now, in keeping up with the universe, what I do is I interview scientists like Kate over here who are doing some research in the field of astronomy and space science. And they try to answer a few questions about the research and how it's going to make an impact in the future. And hopefully that's going to help them, reach out to the public through science communication and also give us something interesting to talk about. So over here, if you want to ask any questions to Kate, if you want to ask some question related to her research, you can put it on the comments, which I can see over here from my window. So if everyone's ready, let's begin with the interview. So Kate, today we've come over here, and as I know that you research about galaxies, right? And that is why we've named this episode "The Sweet Life of Galaxies." And over here, my first question to you, Kate, is that let's start knowing a little bit about your research. So, what is the hypothesis behind which your research is based on?
Okay, so galaxies and galaxy evolution, which is how galaxies change in general, is a really big field in astrophysics, so I'll try to keep it brief. But so we live in a galaxy, right? We live in the Milky Way. And the Milky Way is a star-forming galaxy, which means that it's forming stars on a regular basis. And it also has a very particular shape. It's a grand design spiral. If you look at models of how we think the galaxy might look, it has these very cool looking spiral arms. So that's just one type of galaxy. It's also a very massive galaxy. It has on the order of about 10 to the 11 solar masses, which is pretty big. But that's not the only type of galaxy that we can have. So there are loads of other different types of galaxies, ranging from how massive they can be over entire orders of magnitude, to the sizes that they have or the shapes that they have. So they can be really weird shapes. They can be shaped like rugby balls, and they can also have different levels of star formation. So ours is a star-forming galaxy, but there are also galaxies called quiescent galaxies, which basically means that they're not forming stars anymore. And galaxies need gas to form stars. So basically, they either have gas and they can't form the stars from the gas, or they've just used up all of the gas and they formed all of the stars, and then the stars have just become old and look very red, because basically once stars are old, they become red, kind of like candlelight, because they're not very hot. So that's just a primer on galaxies. Galaxies can actually change, so they can go from being star-forming to quiescent. They can go from being a spiral to being shaped like a rugby ball if two of them merge. And galaxy evolution is the field of science that kind of tries to build it up from when the first galaxies formed within the first billion years of the Big Bang to now, which is about 13.5 billion years later. And what I do is I try and look at galaxies across cosmic time and look at their properties and try to figure out what caused them to die, because there are many different ways that they can die. And even though we've been studying galaxies for like 100 years now, we still don't really understand how they transform from one type to the other. So that's basically it.
So that's interesting. So there are more than one ways a galaxy can stop making stars?
Yeah, exactly. So I mean, just to say a few of them, if two galaxies merge together, then usually all of the gas is driven to the center, and then there's a giant burst of star formation, and then that just uses up the gas. But also the morphology of a galaxy can stop it from forming stars. For example, if there's what we call a bar structure in the middle, where stars align in like a certain shape that basically just looks like a chocolate bar, that can actually stop gas from forming stars. And also, if you have a giant supermassive black hole at the center, that can also stop it from forming stars by heating up the gas, because basically the gas has to cool down and then like form into a cloud and then collapse on itself. So if you stop it from cooling, or you make it move around lots, then it can't form any stars.
So as we know that even Milky Way has a supermassive black hole in its center. So isn't that stopping Milky Way from creating new stars?
Maybe. I'm pretty sure there are people who study this, because actually studying the Milky Way is like an entire corner of like galaxy science, because there's
Right.
basically galactic, which is the Milky Way, and then extragalactic, which is everything outside.
Right.
So I'm not too sure about that one, because some supermassive black holes stop stars forming, but some don't. Again, it's like an ongoing question. But I do know that people have studied the way that stars move around the center of the supermassive black hole to figure out that it was there. So I guess you could also look at the gas near the center. I'm pretty sure one of my friends is actually doing that for his PhD, so maybe you should get him on.
Oh wow, yeah. So you after this you could give me, the reference, and I'll definitely approach them.
Yeah.
So that is your research based on. So basically, trying to predict when and why can a certain galaxy die, right? So is that a good way to say it?
Yeah, I mean, in particular, I'm specifically interested in how the first galaxies to die died, because basically from simulations and theory, we know that it takes a certain amount of time for a galaxy to build up a certain amount of mass and then die. And observations were agreeing with this. But then in the past 5 years, people observed loads of galaxies which had died in like half that time. And they're all just like, wait, how can this happen? This doesn't make any sense. And this was around the time that I was trying to find a topic for a PhD. And I happened across all of this and I was like, wow, this is crazy. I want to look at this.
Wow, that's awesome. So in the middle of everything seeming normal, you have a puzzle over there to solve.
Yeah, I mean, so there's lots of puzzles, but to me, this was the most interesting one.
Okay, so that actually, would be a good follow-up for the second question. That is, why do you choose this topic for research? So going on to the last point, you could elaborate that a little.
Yeah, so from doing certain like labs and stuff in my degree, I found that I was interested the most in galaxies. And then I did a summer internship, which was basically trying to find these dead galaxies, but you could find them because they'd been lensed by foreground galaxies. Shantanu, are you still there?
Yeah, I'm here.
Okay. So they've been lensed by foreground galaxies, and galaxy lensing is basically where there's a galaxy in front of another galaxy, but the foreground galaxy is so large that it actually bends the light. So you can see hidden galaxies because the light is bent, and they end up looking like these sort of circular rings. So
Right.
I was trying to find these dead galaxies that way, and that was my introduction to realizing that galaxies die way earlier than I thought. Because when I was taught about galaxy evolution, you kind of just learn that, like, okay, so there's roughly 2 populations like now in the local universe, like 13.5 billion years after the Big Bang, and that like a lot of them are dead and a lot of them are not, and they didn't really know why. I didn't know that there were also some dead ones way earlier, and I found that very interesting. And then I basically was trying to find somewhere that I could do my PhD in this. And then I did.
That's awesome. So when you said that you were using gravitational lensing to find galaxies that were old, so is there some bias, like most of the foreground galaxies are old or most of the background galaxies are old? Is there some kind of bias that would help you do this?
Well, most galaxy foreground lenses have to be quite close to us.
Right.
And they also have to be really massive, but they also tend to be really old. So most of the foreground galaxies are like these old, massive, dead galaxies. And then so it basically what I did was I found a lot of these that were nearby, and then I wrote an algorithm that would look within a certain area of them where you would expect to see a galaxy that was lensed. But there is kind of a bias in terms of the fact that when you're just looking at singular galaxy lensing, that is like just one galaxy lensing another galaxy, it's really good for finding star-forming galaxies that have been lensed because they're very blue. So you have something very blue surrounding something that's very red, and it's really obvious. But when you're trying to find something that's red around something that's very red, it's really difficult.
Yeah.
So you kind of have to take that into account. And the conclusions that we came out from this project was that it's either really, really rare that this happens, or it's just impossible to tell because you basically can't tell these things apart if they do happen. And it's actually a lot more common that people use cluster lensing to look at galaxies instead. That is where
that's interesting.
Like a galaxy cluster that is really big and then lenses lots of stuff. But that's a lot messier because there's all kind of like physics that happens that make all of the galaxies that are lensed just look like really weird, like squiggly lines instead of just like a perfect circle.
Right. So I've actually seen a few of those pictures. So where the galaxies look like S's and complete
Yeah,
O's and stuff.
yeah, and scientists have to create these like crazy algorithms to undo all of that,
Mhm.
and I like the assumptions that you have to put into your models is actually terrifying.
So what language do you prefer for making the algorithm?
So I primarily work in Python, although I have used Fortran and Mathematica before, but I find Python is the best for what I do, because it's very easy to learn and there's lots of astrophysics packages that are built into it. And the data visualization is very easy with like Matplotlib and stuff like that.
Right. So I've actually heard a lot of researchers prefer Python for especially in astrophysics. So I also wanted to ask that some places I've read that C++ is actually better than Python. So do you have a opinion on that?
It depends what you mean by better, because it also depends what you want from your code.
Like,
So I guess if you wanted something that was like very fast, then you might want to go with one coder for another. For example, if I was writing a simulation, I would go with Fortran over Python probably. But I mean, yeah, I guess it also depends on how you're writing your code, because I think C++ is maybe object oriented. I don't know. I didn't take like a computing science degree. I've never written anything in C. So to me, I think Python is the most accessible for astrophysics, just because like it's very easy to
right.
learn, and there are lots of packages online that will do things for you, so you don't have to write all these complex algorithms.
So that's going to be very helpful if you already have half of the work done for you.
Yeah, exactly. Like a lot of people will develop software in Python during the course of their career, and then they just end up like making their career out of that, which is what my supervisor did.
Oh, wow. So now I think it's a good place to know about how are you carrying your research. So what's the methodology that you follow?
Like, how do I do it?
Yeah. Yes.
Okay, so a lot of what I do is right now is like data exploration of catalogs of galaxies that have been created from images. So mainly a lot of coding and data visualization. But I also do other things like write telescope proposals, which is very intense and hard. But yeah, the main thing that I do mostly is I work in Jupyter notebooks, and I'll do data exploration, and I'll create lots of plots to try and figure out what my data is saying. I also spend quite a lot of time reading scientific papers to figure out what is going on in the field, or like trying to recreate different methods that people have done, or just flicking through to see what parameter values they used. And then another thing that I do is I spend not quite a lot of time, but like some time in meetings. So I'll discuss my research with my supervisors or collaborators. And once a week, my department basically gets together on Zoom, and then we like talk about our research and we ask each other questions with stuff that we're stuck on. So it's kind of split between reading, collaborative work, and coding.
So that's awesome. So you right now mentioned that you also write proposals for telescopes around the world. So how does that work? Uh,
So basically, you want a question that you want to answer, and how you're going to answer that question is basically by using a certain telescope. So, for example, say I want to know if a galaxy is actually dead or not. One way to do that would be to measure how much gas it has using something like the Atacama Large Millimeter Array, ALMA, which is a fantastic telescope. And so what you would do is you would basically get your sample of galaxies, and you would figure out how long you would need to observe them for and like in what wavelength. And you would do all the technical stuff, which is a lot of the work. And then you'd also need to write anywhere between like 1 and 5 pages of like scientific justification, because how telescope proposals work is that there's a board who like decides if you get the time or not, and it's just made up of like anonymized experts. So I think most of the time it's double blind. They don't know who you are and you don't know who they are, but they will read all of these proposals. And if they think they're important or convincing enough, then you get telescope time. It's very competitive because obviously there are lots of astronomers and not many telescopes. And people usually tend to just so there are 2 telescope proposal seasons a year, and people will usually just do nothing but write telescope proposals for like a month or 2. But I think the general rule of thumb is that you probably shouldn't spend more than like a few weeks on one proposal, because a lot of the time it's going to get rejected just because there's so much competition. And so you don't want to spend a significant amount of your time investing into something that you may not get returns on. So it's quite stressful.
Right. Obviously, given the competition, and as you said, there are so many astronomers and so less telescopes.
Yeah.
So what are the telescopes in the past that you've been involved with?
So I haven't really written that many proposals, but I was so usually how it works is there's a principal investigator, which is the main person, and there's lots of co-investigators. So one of the other PhD students in my department got a successful proposal through on the James Webb Space Telescope to look at like some of the first galaxies. And so I ran some simulations for him to show that we could like get the properties from the spectra. And so I'm a co-I on that. And when we eventually get the data, I'll be involved in that project. I also submitted a proposal to look at a dead galaxy with the Very Large Telescope, which I think is in Chile. I always forget where they are. And then I've also been part of a team that submitted for time on Hubble. So I think the main ones in my field that we submit for are James Webb, Hubble, ALMA, VLT, and then one called NOEMA, which is kind of like ALMA.
Right, so it's mostly infrared lights that you're studying, is that true? Or a little bit of optical also?
It's combined optical and infrared, because the galaxies that I'm looking at, their light has been stretched because the universe is expanding. So they've been redshifted. Right. So the light in the optical has been shifted into the near infrared, and the UV light has been shifted into optical. So this is why we're really excited about James Webb, because it's an infrared space telescope.
So I guess you were one of the most heartbroken people when James Webb was again postponed for launch.
I don't think I was heartbroken. I think I was just like, well, that's not really surprising at this point. The funny thing is that when I first applied for PhDs in like winter of 2019, all of the positions I applied for were like, study the first galaxies with James Webb. And even then I was like, that's not going to happen. And so we have plans for the final project of my PhD to use James Webb data, but I'm not expecting that to happen. It would be a bonus, but I'm not expecting it. And to be honest, there's still lots of data that we have right now. For example, the data they use right now is from something called the Cosmos field, which is the deepest and widest combination of the sky that have basically every telescope on Earth and in space pointed at it. So a lot of people use this field for galaxy evolution.
Oh, so that's awesome. So are there, they're like these free databases of Gaia and Hipparchus. So are there such databases for galaxies also, where any new researcher who do not have the access to these telescopes could use the data for?
Yeah, so usually what happens when people do giant surveys with data is that they will do data releases, and some of them are only available to the scientific community, but a lot of them you can just go and get it off the internet yourself. A great way to get if you're just interested in looking at like what galaxy spectra look like or what galaxy images look like, a great way to start would be to looking at SDSS, which is the Sloan Digital Sky Survey. And they've mapped basically, I think it's like half of the entire sky and looked at basically every galaxy in the nearby universe. And I think it's finished now, but they have all of their data online for anybody to use. And I think it helps if you understand SQL, but you don't really need to know SQL. You can just go on some of their pages and just click like, give me a random spectra, and it'll give you a random spectra. But with most other things like Cosmos, like it will be available for free online after a certain amount of time.
Wow, so that's awesome, right? So I love this thing about astronomy, that everything is so collaborative. That a lot of things are over there. You just need to go out and search for the database. So moving on, Kate, the fourth question that I have for you is, could you tell us any interesting thing or things about your research? Something that must have come up during this study.
I think the most interesting thing to me is that for these first galaxies that died, people can't really figure out what exactly killed them. And one problem about this is that we don't really have the data resolution, because we need things like James Webb, and probably something even better than James Webb. But what the data suggests is that they form stars in an extreme burst of star formation, like forming thousands of stars in a year, which is insane. But then they also managed to kill that many stars, or not kill the stars, but they managed to stop forming stars at like just as fast as they form them. So imagine like a ridiculous explosion of star formation, and then as soon as you like look back a second later, it's all stopped and it's dead. So I think that's like the most interesting thing, is that there is something that is causing incredible things to happen on incredible timescales so early in the universe, and we don't see this later on in the universe. People think it's probably black holes, but obviously there's like not much way to tell, because a lot of the inferrations, I don't know if that's a word, a lot of what we infer from our data is based so heavily on assumptions and models that basically until we can get really cool space telescopes that are like huge and look at one galaxy for like hundreds of hours, we won't really know. So I think the other interesting thing is that we've managed to obtain so much information from so little data.
Yeah, that's actually very interesting, and I wanted to follow up on that by asking that are there any current theories that explain how this could have been possible? That something that's creating so many stars every year suddenly dies.
So I don't know if there's a theory for how they form stuff in such intense bursts of star formation, because that's something that I haven't really looked into so far. But one paper came out recently that suggested that there were lots of galaxies all in a cluster, and then they all suddenly started starbursting at the same time, and then they merged, which caused it to die just as fast. And this was a really cool paper, except that they gave absolutely no explanation for how all of these galaxies would suddenly start starbursting at the same time. So obviously this is still ongoing research.
Right. So, and how do you think future telescopes could answer this? Like, how can James Webb contribute to answering this question?
So the cool thing about James Webb is that you can get the spectra of a galaxy, so you can look at all of the light in high resolution, which is something that we can kind of do with the best telescopes on Earth. But to put it into perspective, to study a dying galaxy 200 billion years after the Big Bang, I don't know the distance scale, so just think in time scales. It's very far away. Basically, to get a poor resolution spectra of that, just to confirm that you know that it's like at that redshift, you need 1 or 2 nights on the best telescope in the world, which is extremely competitive to get. You're saying, please give me 12 to 20 hours to just look at one galaxy to just confirm that it exists. Because the data that we have originally is just photometry. So you just have points on the spectrum instead of the entire spectrum, and you fit a model to it. So you're not even sure if it's real. So James Webb will obviously help us confirm that these galaxies exist. But because there's no atmosphere in the way, we'll also be able to look at things like absorption lines and emission lines. And from these lines, you can tell if there's a black hole there, or like what sort of things are going on, or like how long ago did the star formation stop, with a lot more certainty than just like from models.
Wow. So I, for one, I'm waiting so much for James Webb to launch. One interesting thing that I'm also waiting for is for James Webb to study Uranus and Neptune, which have been the most unstudied planets in the solar system. So hopefully NASA is going to, do all the tests that are pending and just launch it as soon as possible.
Yeah, I hope so too, because then I might be able to use it for my PhD.
So fingers crossed for you also.
Yeah.
So moving on to the next question, that is, and I think a little bit of this has already been answered, that what kind of equipment do you use for your research?
So technically I use telescopes, but I don't actually use them. I just use the data from them. But my coding is not very intense, so I just use a laptop. But sometimes I'll use like online coding servers like DeepNote, where you can share like Jupyter notebooks with people. I also use a good old-fashioned pen and paper and a whiteboard for when I'm just trying to flesh out ideas. I don't know if software also counts as equipment. Because I could also say what. So, okay, yeah. So I use, in terms of organization, I use something called Zotero, which organizes papers, which you can just go back and access them and see all the notes that you've made. I also use Overleaf for writing papers. I use a lot of different packages that have been written in Python to do science. And then I also use things like Google Calendar and Todoist, because being organized is a massive part of like doing research and doing a PhD, and like it's up to you to do it. So I rely on them a lot. Oh, and
So
then
I
also
really
Zoom.
hope that Right. So I really hope that those apps, they're going to help the viewers to organize everything, because lately even I've been trying to organize, even stuff from university. Apps like these can help you. So early in the university, you start going through papers, and you want everything of that to be in place. And then obviously the pen and paper is the best thing. It always there. So, Kate, till your research and starting from, whenever you started your journey of university, what was your academic journey like?
From like university onwards.
Yeah, so like after you were from your bachelor's, we could say.
Okay, so I did an integrated bachelor's and master's, which is called an Mphys in the UK, which is really common, which basically means that you do the same credits from a bachelor's and a master's, but you don't graduate in between. So I just did 5 years in Scotland, but usually it's 4 years. And throughout this, I also did lots of summer research internships and loads of different things. So I worked at the observatory at my university. I did one in cosmology. I did quite a few in experimental particle physics, because basically from when I got into physics as a teenager, I couldn't decide between particle physics and space because I like both of them. And then ironically, I went to work at CERN for a month, and that really put me off. And then I discovered Galaxies. And then I did this final internship in Galaxies. And then I started my master's year. And I ended up doing my master's project also in Galaxies. So yeah.
So I guess you just said that you went to CERN and that put you off about particle research.
Yeah.
So why did that happen?
Okay, so maybe it was a particular experience that I had, but it was like a combination of a few things. So I was one of the things that you can do at CERN is you can apply to use their facilities. And so I was part of a team that was testing a new type of particle detector. And so they like shipped it from the UK to CERN to use their facilities for like 6 weeks, but they had a set time period, which meant that they only had like that amount of time to get stuff done. And there was a team of like 30 of us, and there was like me and like 5 other interns who were helping, and basically we were just there to help with like anything that they needed. And it was a really, really cool experience because we were literally like helping them test a particle detector at CERN. But also one thing that I gathered from that, and from also my friends that work in experimental physics, is that when you do lab-based work, it dominates your entire life. Like I found it very, very difficult to get any time off. I found it difficult to make time to like go to the gym and do these other things. And having work-life balance is really important to me. And although I really enjoyed working with the detector and like doing the practical stuff, I knew that if I wanted to go into that kind of career, it would involve basically sacrificing a lot of things, because lab-based work is very chaotic. And sometimes you just have to spend like several days trying to get your equipment to work when it won't work. I also realized that I like particle physics from like a broader sense of view, but when you actually get down to like doing like the research on a computer and like having to do like lots of quantum mechanics and stuff, like it wasn't for me. So it was a cool experience, but I'm glad that I have it because it meant that I could actually realize what I wanted to do instead.
Right. So that was a fortunate experience, we could say, that helped you choose between two things you were very passionate about.
Yeah.
And this project on Galaxy that you made after your master's, what was the topic of that project?
You mean the internship that I did? Or during my master's?
So during your master's, actually.
Okay.
You said you did a project on Galaxies.
Yeah, so I was looking at galaxies in the local universe called post-starburst galaxies, which is a special type of galaxy which has just experienced a starburst that was then very quickly quenched. And these are very rare in the local universe, but they're like less rare at higher redshift. And there's been some study of these galaxies. My supervisor was like an expert in them. And it's been found that a lot of them are actually experience a merger, like a galaxy merger, or they had one in like the past few giga years. And basically, she wanted me to look at a brand new sample of these galaxies, and then look at the imaging, which is like deeper than any imaging before, and to use a code that would measure like the merger fraction, to see what were the morphologies of these post starbursts, and like maybe it caused the starburst or maybe it caused the quenching. So yeah, it was pretty fun.
Oh, so that all your research on Galaxy has been around topics that has been very new.
Yeah.
So I really love that idea. So I think everything deciding your postdoc topics, was it easy or was it difficult deciding your topic about what you wanted to do PhD?
I think I more grappled with this when I didn't really understand if I wanted to do particle physics or astrophysics. But once I found out that I like galaxies, it was very easy for me because I knew that I wanted to study galaxies. I did have this grappling between studying nearby galaxies and far away, because basically nearby galaxies, you get lots of data, you get beautiful spectra, you get gorgeous images, you can find out so much about these galaxies, which is really cool. But to me, I felt like the biggest questions were the ones of like, how did the first galaxies form? How did the first galaxies die? These are the things that we don't really understand. And so I was trying to grapple with, okay, do you want to have like not so great resolution data and study like these really big questions, or do you want to have great resolution data and study the more like focused questions?
So I guess over the course you got to study both kinds of data.
Yeah. And hopefully with James Webb, maybe I'll get some higher resolution data of these ones too.
Hopefully, yeah. So James Webb, just launch it as soon as possible. So coming up to the next question, that is question number 7. So, Kate, what can be the implications and follow-ups that result from your research?
So the questions that I'm trying to answer right now, it's kind of threefold. So with these galaxies that die very early in the universe, there's been a lot of debate about how many there actually are. And the data that I have is like the best data that we have so far that can tell us about these kind of statistics. So the first thing we're trying to figure out is the statistics of like how many there are and like with how much certainty we have. Which also basically answering any questions about these galaxies has like repercussions for like the entire galaxy evolution as well. The other thing I'm trying to figure out is how long ago they stopped their star formation. This is very difficult to do because obviously we don't have the entire spectra for each galaxy. We just have photometry where we just basically have one point like every so often along the spectra. And so I'm fitting models to these and then inferring the star formation history, which is basically the star formation rate of a galaxy as a function of like look back time. And so I'm trying to figure out the quenching timescale. And we know that certain things take certain amount of times to quench. So if I can figure out the quenching timescales, that could maybe give us an idea of what could be causing these galaxies to die.
Wow. So have you already thought of any follow-up questions that you're going to answer after this research is done?
Like with my PhD?
Yeah, related to this particular, the research that you're trying to understand the question time scales of galaxies. So while doing it, have you already come across a question that you would like to follow up once you're done with this, that you personally would like to follow up?
Yeah, so one thing that I'd really like to do, I don't know if I can do this during my PhD or afterwards, is look at the gas fractions of these galaxies with ALMA, which would basically tell us whether they have gas and it just can't form stars, or whether they just don't have any gas at all. Because ALMA can measure dust, and then we know that there are certain relationships between dust and gas, and we can figure that out. The problem with that is to get time with ALMA, usually you need to have your galaxy already confirmed at that redshift, which requires time with like Keck or James Webb or something. So this is like a very involved project. So I'd really like to do that at some point.
Right. And I just wanted to ask this, since you said that you wanted to find out whether a galaxy has gas and still can form stars, or it does not have any gas at all. So is it possible for a galaxy to not form stars even though it has gas?
Yeah. So if you have gas, but it can't form stars. That basically means that there's something that's preventing the gas from forming stars. So for gas to form stars, usually gas is just like chilling in a cloud, and then the cloud will collapse in on itself on gravitation because of the gravity, and it has to be collapsing more than the gas has energy. And another way of saying that is the gas has to be cold, because if it was really hot, it'd be moving a lot and it wouldn't be able to collapse because the movement would outweigh the collapse. So if you heat the gas from, I don't know, friction, like turbulence, which is like one theory, or a supermassive black hole, that could heat the gas and stop it. Also, if you make it move really fast, then it can't collapse. So turbulence. You can also shoot the gas out of a galaxy, because these supermassive black holes are supposed to have these giant jets, but somebody recently proved that that doesn't really happen in some galaxies. So yeah, there are lots of different ways that you could have gas, but you're not forming the stars.
Wow. Okay. Thank you so much for answering that question. So I think now we'll move on to one of the questions that I'm waiting for. Is that, can you tell us something interesting about the main object that is the focus of your research? So I guess over here it would be galaxies.
Yeah, so the main object of my research would be these first-to-get galaxies. I think something that I haven't mentioned so far is their sizes. Like, take a guess, how big do you think they are compared to something like our galaxy?
The older galaxies?
Yeah.
So thrice the size of Milky Way?
Okay, so I believe the Milky Way is like several hundred kiloparsecs wide. I'd have to check that. The size of these galaxies, which has been measured, is about 1 to 3 kiloparsecs. So if you imagine our Milky Way is about this big, and then you have something which has the same amount of stars, which died gig years ago, is like, I can't even, like,
Well,
it's like...
that's actually very small.
Yeah, they're dense.
I thought the galaxy made in the past, they had so much of gas, so they would be much bigger.
So they have just as many stars, but they are really, really, really small, which is crazy. Like, it doesn't make any sense. And people think that you have like these very compact centers, and then over the time of the universe, they accrete other galaxies which are small, and then they become the really big, like massive elliptical galaxies that we have today. But it's just crazy that they are like ridiculously tiny, but they still have the same amount of stars in them.
So, assuming if there's a planet or someone to observe it, they would be seeing much more stars in the sky, right? The night sky would be much more bright. Is that right to say? Because of the increasing density?
Yeah, I've never thought about it like that, actually. But I mean, another interesting question to ask would be, like, when did the first planets in the universe form? Because I believe it took like several billion years for our entire solar system to like equilibrate to some point. So yeah, even thinking about whether there would be like planets in these galaxies is a crazy question.
Wow. So that's something new, and that's actually really surprising that a galaxy just as big would be so small.
Yeah.
So I would try to, make a comic on this, that what would the night sky from that place look like?
That's so cool. I would love to see that.
Okay, so as you said, you were talking about CERN, and you were saying that you realized that if you were into lab-based research, it would be very hard for you to find a time for your personal life and other interests that you have. So even in this field of research, how do you balance your research life and personal life?
So I find it pretty easy now that I'm doing a PhD, but during my undergraduate and master's, especially during my master's, it was really difficult. But I think like carving out certain points of your week where you have to not be working is really good. So I do this by doing sports. For example, at university, I was part of a weightlifting club, and we did that like four times a week. And also making sure that you like actually see your friends. But I mean, now I have set working hours. I work from between like 9 till 5 every day. And I don't work outside of that unless I have to. So like during telescope proposal season, obviously I have to, or like if I have like deadlines, or like maybe I'm writing a paper or something, I would maybe go outside of that. But I learned from like basically working nonstop and not getting enough sleep and like not making time for anything else during my master's, that you burn out really, really quickly, and it's not really possible to maintain working yourself to death for a long time, because like you do have to pay for it at some point. And it's quite painful. So now I'm very strict about having a work-life balance.
So what do you do in your normal average day apart from research?
So now that we're out of lockdown, I can actually go to the gym. So I go to the gym. I also recently started playing ultimate frisbee. I just like see my friends. I spend some time with my partner every week. Yeah, exploring Copenhagen. During lockdown, it was more like, okay, I'm logging off my computer. I'm gonna log into my video games now.
So what video games do you play?
I got really into Stardew Valley, which is like this farming game. It's the most adorable game ever, and it has like a really nice storyline, and all of the characters are really cute. And you can also design your farm however you want it to be. I really recommend it.
My mom's hooked to a game like that. She actually got mad at me because for some reason the internet it was not uploading her game. Everything else was working, all other websites were working, and then she got so mad.
Oh no.
So the next question that I want to ask you, Kate, is that what are your tips to communicate a research under 5 minutes? So we have these long research papers that have so much of detail in them, and even sometimes even I burn out reading just one paper. So if you were in a meeting where you had to present your results, how would you do that in under 5 minutes?
Okay, so I would say it boils down to three things. You want to explain what your question is in relation to the bigger picture, because that helps people contextualize things. And you also want them to understand why it's important and why the question exists and why it should need answering in the first place. So that maybe takes like 1 to 2 minutes, because you basically want to set your research in the context of everything else.
Okay.
And then in like the simplest way possible, stripping out like all of the unnecessary details, explain how you did your research, or what the methods people used in a paper. And then the final minute would be like the 1 or 2 conclusions that came out of it and what this means for the big picture. So it's kind of like telling a story, I guess. But I think the most important thing is to always set it in context of what already exists. Because if you start talking about something in detail, people will be like, wait, what? But like, why is this important? What is this even related to? I'm so confused.
So building a context to something that they would understand easily is more important.
Yeah.
So would you include the maths in 5 minutes, or would you keep it out?
Would I include what?
Would you include the maths that comes up in your research, or would you keep it outside? Outside
I would definitely keep it out, but there isn't a ridiculous amount of maths in my research anyway. There's a lot of statistics, I guess. I would definitely keep it out.
So I guess you're in team. Are you a maths person, or are you not a maths person?
I used to really not be a math person, and I don't really know how I feel about it now. But the funny thing is that when I was about 13, my least favorite subjects were maths, physics, and chemistry. And then I ended up taking them for my A-levels. But yeah, I was never very good at maths. I hated maths. I did not find it interesting at all. I was not very good at it. And then when I got interested in astronomy and decided that I wanted to be an astronomer, literally everyone was like, you need to do maths to do that, right? And I was like, well, fine then. So I basically just committed like 2 years of my life to like not being bad at maths. And I did every single question I could possibly find. I did every single past paper. Every time that I had any problem that I didn't understand, I would go and ask my teacher. There was no like, I didn't left like anything like to the side. Like basically, if I didn't understand something, I would like keep doing it until I understood it. And so I went from like my teacher being like, wow, you hate maths so much, to like on the day I got my A-level results, then being like, you got the best score in the year. And I'm like, what?
Wow. So that's a great roller coaster journey with maths.
Yeah. Having said that, one of the reasons I didn't go into particle physics, because there's a lot of quantum mechanics, and the maths in that is a very different type of maths, linear maths, which is not my thing so much. And the thing I like about my research now is that it's not super maths heavy, apart from statistics. So I would say that although I overcame my problems with maths, I'd still rather not do it.
Same team. I totally agree with that.
Yeah, but I mean, if you really want to be a scientist or an astronomer and you think that maths is going to hold you back, it won't. Like, it is possible to not be a maths person and then like become a maths person, I guess.
So just as you said, keep solving the questions. I guess that's a good way to like it. So once you start solving the question, you see, oh wow, okay, I'm good at it.
Yeah.
So, given of all of this hard work that you put into your work, and even during masters, you were, as you said, you were mostly burnout, and even these days you have so much of meeting and research papers to go through. So, how do you deal with mental blocks that come up during the research and take care of your mental health?
I think this is something that I really struggled with because usually when I have mental blocks and it's not burnout, then I kind of just force myself to work through it. But nowadays, I think I'm a lot more lenient. Like if I'm just having a week where I'm finding it very difficult to do something, I'll find something else that I can be productive with. Or I will do other things, like have discussions with other scientists about their work. Or like recently I've been doing more like Instagram stuff, I guess. So if I'm finding it hard to like concentrate or anything, I will try to make myself walk away from it for a bit and then come back. Because if you're just trying to keep pushing through something and you're not getting anywhere, then you should probably just take a break.
Right. So that's actually helpful because even certain research have shown that if you're continuously doing something, your brain starts paying attention to it.
Mm-hmm.
So that brings me to the next question, Kate. That is, how would you explain your research to a kid? I guess
this
would
one
be
is hard. God, I've never actually explained my research to a kid, so I guess this is a good question. So I would basically explain that we live inside a galaxy, and a galaxy is basically just like a big city of stars. And in order for the stars to exist, there has to be ingredients for the stars, which is gas. And there are lots of different types of galaxies, and much like like humans and animals and plants evolve over time, so do galaxies. And what I do is I try to figure out the evolution of these galaxies. I don't know if that would make much sense to a kid.
But that did sound simple. That took away a lot of complexities in the question.
I'm glad.
So you did answer that well. So that brings me to the next question. That is, what is a major problem or obstacle that you faced during a research to get the data, and how did you overcome that problem?
I think the biggest problem in astronomy is that we're always waiting for the next generation of space telescopes to launch. The problem is that from conception of these space telescopes to when they actually launch and get data can be something like 25 years. And so astronomers are basically always trying to work with subpar data to them because their understanding of space advances way more rapidly than we can actually build the equipment to get out there.
Right.
Yeah, so I guess one of the obstacles is always trying to get the most out of the data that you currently have, because you're going to have to wait ages to get the next lot of data. By the time you have the next lot of data, you'll already be like, well, it'd be great if we had this even better space telescope.
So this is a never-going circle.
Yeah, it's an ongoing circle.
And apart from this general problem that everyone in astronomy would come across, in your research specifically, while getting the data, or while going through the spectrum that you received, was there a particular common obstacle?
I think knowing how to interpret your data can be really difficult because a lot of definitions in astrophysics are defined differently by different people. So I think one of the major problems in my field is the way that people actually define what is a dead galaxy, and people are defining them and selecting them in their catalogs of galaxies in completely different ways. And so it can be really difficult to compare between different literature because they've all done it in completely different ways. And so you don't know how much is uncertainty about what we actually know, and you don't know how much is systematics from the way people are doing the science. I guess one way that we can overcome this is to have more communication with each other. But the problem is that because of the telescope thing, this area of science is also quite competitive. And so there'll be multiple different groups working on exactly the same thing, but they won't talk to each other because they're competing against each other, which can be quite frustrating. Like one of the common things. So would you say this is a good? Sorry.
I'm sorry, I interrupted you. I was asking that would you? What's your opinion on this? That people, even if they're in competition, we usually think of science as more collaborative. But the idea of being in competition stops them from, talking to each other and sharing ideas. So, what's your opinion on that?
I think it's a tough problem to solve because more and more people want to do astrophysics, and there are so many astronomers, but there's only so much data. And so I'm not really sure how to solve the problem because it basically just boils down to so many people trying to figure out the same thing, but we're all competing for the same data. And so something would like fundamentally have to change about the way that astrophysics happens in high redshift galaxies for that to change. And I'm not really sure how it would happen. It would be nice if it did.
So over here, these are more, we could say these are more problem of the way the science is done rather than something related to the equipment or something like that.
Yeah, and I think in general, academia like can be quite toxic because of like a multitude of different reasons.
So moving on from over here, we come to the next question. Speaking about academia, as you just brought it up, so assuming the research takes you into academia and teaching, what are your opinions on that? And are you comfortable in the classroom? And what are your hacks to being a good educator?
So I haven't really done that much teaching, although I have to do some during my PhD. But when I've just been like explaining things to like members of the public, like doing science outreach, or like when I was in high school, I mentored other students on physics and maths. I found it really rewarding, and it's also really fun. And so I know a lot of people want to do research, but they're like, oh, I don't want to do teaching. And I'm like, oh, I would love to teach people about space. So I actually signed up to have a summer student for the next 10 weeks. And I'm already finding that so much fun because it's just really rewarding teaching people stuff.
So what are your hacks to being a good educator?
I would say 2 tips. Never assume that just because you think something is obvious that somebody else does. I say this because I've had a lot of teachers who would just assume stuff or say like, if it's not obvious, then you're stupid, which is a massive barrier and can make people feel even worse about the misunderstandings. So always try to get down to the person's level, find something relatable. So that leads into the second tip, which is use lots of analogies. So when I'm trying to talk to people about my research and they are not scientists, then I'll always try and use analogies. I'll be like, okay, so what do you know about this? And they'll be like, I don't really know that much. And I'm like, okay, great, I'm going to teach you. And then I'll like try and make it relatable.
So that's actually a good hack because, it's so, because being professional, you're using this, jargon every day that you know everything what it means. And for you, something is very obvious. And when you talk about it to someone whom you assume should have the same knowledge, you may sometimes be a little toxic. And it does happen that teachers take their words, students take it very seriously. And someone who has the quality of doing good in a subject may still drop it just because of that.
And I think a good teacher can be the difference between a student going on to finding like a lifelong passion in something, or that student like dropping out of the class and being like, wow, I never want to learn about that again.
Right. I've actually had students like these. So when I teach, there are students who absolutely hate science or absolutely hate maths because the kind of way that they're taught in schools makes them hate the subject.
Yeah, that's how it was for me. I never had a good maths teacher until very, very late in high school. And then the maths teacher that changed everything was actually this really cool guy who used to work in like a Heinz beans factory. And he always used to talk about baked beans. And he was always so excited, which is different to every other maths teacher I'd ever had. So I think enthusiasm is also really important.
Right, excitement is contagious in the class.
Yeah.
If you're excited about a subject, students get as well excited about it.
Yeah, exactly.
So over here is another one of my favorite topics, questions to ask you. So what is the most recent new thing / news you learned related to any topic? So it could be outside astronomy also.
Okay, so I'm reading a book right now about chaos, which is this whole incredible science about like unpredictability. And you know how like weather patterns are chaotic and like we can't predict them. One really cool thing is that I don't know if it was a real experiment or a thought experiment, but somebody measured like the coast of Britain, and then every time that they like zoomed in, it would become longer and longer. And actually the catch is that it's infinitely long, because every time that you zoom in, it's going to become even longer. Because you're counting things that weren't there before.
I think that's a thought experiment.
Yeah.
But that's actually a very wild idea, because these kinds of infinities, they just blow my mind. I think it's the same as there's this one analogy about a rabbit and another animal racing. So they keep covering a little bit distance, but it never is able to reach the other animal in front of it. So right now I'm being very vague. I realize this because it's very the idea is very distributed in my mind right now. But it reminds me, I even read about the same thing. So is the book on chaos by John Gleick by any chance?
Yeah, it is.
Right. So I think I read it in the same place.
Nice.
So carrying on from that, it brings me to the question. If it was not for this subject, what would you choose to do in life?
I'm not entirely sure. But growing up, I always wanted to be like an artist instead of being an astronomer. And actually how I got into astrophysics was that I would just draw space. Like I would do loads of paintings of space and like the Milky Way and Jupiter and things like that. So maybe art. But I also really like being around people, and art can be quite lonely. So maybe something people-oriented, like being a teacher, or working with other people to like solve an important problem. Like I have thought sometimes about like going into something to do with the environment, because that's also something I really care about. So maybe that.
So are you involved with any local groups or activities regarding the environment?
Not right now, but I tend to try and align my lifestyle more towards environmental friendliness. But I also have a lot of eco-anxiety, so like environmental activism is something that I have like stayed away from so far, because I find like just existing in the world right now with this whole like environmental stuff very exhausting. So I really commend anybody who does all of that activism. Yeah.
So as you said that you used to paint galaxies and Jupiter. So I would just say that if sometime you get a hold of one of those paintings, do post it on Instagram. I would like to see those paintings.
Yeah, I will. I've been thinking about going back and finding them all actually.
Okay, so that brings us to the question 17, and that is is there any particular piece of misinformation or pseudoscience that is common and pisses you off?
I think there's a lot of pseudoscience out there, some more harmful than others. But I think the main one for me would be toxic diet culture, and all of these like diet teas and all of this kind of stuff, or like detox your body by not eating anything for a week. And there are a lot of companies that make a lot of money off selling these products, which are actually very harmful. And I think there needs to be more education about what constitutes a diet that like your body can live off, or like in general, stopping all of these like toxic ideas that are floating around, that like you have to be a certain weight or you have to look a certain way, that like healthy is not one body size. So yeah. it really annoys me, all the pseudoscience around like diet culture.
Right, and in the middle, there was also this really bad craze about toxins as such. So people started calling there are chemicals in food, but they forget to realize that chemicals can even water is a chemical, right? So it's
Yeah,
about the
exactly.
quantity that is there,
Yeah,
right? It's the
yeah.
quantity that makes it toxic.
Yeah, I think a lot of this stems also from misinformation. Um, and it definitely like stems back to how people are taught in school, and how they're involved in how science relates to their day-to-day life.
Right.
Yeah, for example, like, I mean, technically water is a chemical.
Right. So people talk about adding preservatives, and everything should be natural.
Yeah.
So the idea of natural, I think, has been a very big marketing scheme.
Hmm.
So, Kate, moving on from that, what are your views on science communication? And do you have any experience with science communication?
Okay, so this kind of is related to what we were just talking about, but I think science
Right,
communication is really important because there's kind of no point doing science unless you can explain to everybody else what it means, because
right,
only scientists really understand what it means, and you have to make it accessible to everyone else. And this is important in so many ways, not just explaining how astronomers do their work, and why it's interesting, but also science communicators are sort of the go-between between the people who decide what policies we should have to protect us all from the pandemic, and the science communicators are going to explain that to the people who make the policy. So it's incredibly important. And it's also incredibly important that people are educated about things, from, like the type of food that they eat to like vaccines and things like that. Like I know there are a lot of people who don't want to get the vaccine because they're afraid or they don't trust science. And I think that is down to the combination of fake news, but also a failure on the part of scientists to communicate the science. So it's imperative. And a lot of the science communication that I've done in the past has just been with astro, with like volunteering at observatories and open days and things like that. But astronomy is also kind of like a gateway to the rest of science. So you bring people in through astronomy, and then you can start teaching them about everything else. So
right.
I think it's really important that way, because you get them interested in something that they're like, you've seen the night sky, you like looking at the moon, this is cool. You start teaching them about things, and then you can also open their mind to other things as well.
Right. And I also think there's this, I did not know there's a proper name for that. It's kind of some uh, disorder something, but it said that in the scientific community a lot of scientists who are professional and doing research, they think of science communicators as, if I could use the word, failed scientists, right? So a scientist who doesn't do well in research becomes a science communicator. So that's also very widespread, that I actually learned about it last year. So I think that is
Yeah.
one notion that needs to be changed.
Yeah, I think that's also really sad, because I think they're misunderstanding the like incredible skill set that you need to actually communicate science. Like it's one thing to just do science, but it's something else to explain to a wide variety of people, through a wide variety of media, like how that science is done and why it's important and how it affects them. Yeah, I think the other thing is also that a lot of people who do science communication leave academia, and leaving academia is seen as like a failure,
Right.
which is not necessarily true at all. So yeah, I think that also needs to change.
So scientists, I guess these days the younger scientists, they are more involved in science communication. They are more passionate about it.
Mm-hmm. I think it's also easier
Uh,
with social media, with things like Instagram and TikTok. Like you
right.
can,
So you have all the tools.
yeah, like you don't have to say to someone, you should read this book. You just be like, watch this 15-second TikTok video.
Yeah. So I've not been on TikTok, but I have these some great science communicators on Instagram who also post on Twitter. So it has become so easy. So people, if you're following the right people, you can find all these interesting trivia's and some science communication in between all the other videos that you hear.
Mm-hmm.
So, talking about science communication and good science communicators, could you name one scientific figure who's a figure of inspiration for yourself, and why?
I have a few, but I think someone who's really important to me and who is an inspiration is astrophysicist Rose, who I think you also interviewed.
Right. Yeah.
And she's sort of like an astro big sibling to me, because I mean she does really, really cool research, but also like she communicates it in the most amazing art, and she's also balancing like being a parent whilst doing a PhD during a pandemic, and she's just such a kind person. So she's definitely a massive inspiration and role model to me.
That's awesome. So Rose is actually a very great scientist, and I loved talking to her about her research. And it was actually her comics that I came across when I was not doing anything, and that gave that. So she does art, and I should also try that. Even I like art. So Kate, I guess she's inspired both of us. That
Wait, so you started making comics because of her?
in a way. So basically, my best friend suggested me to try something new. He said it was in the pandemic and we had a lot of free time. And while I was trying to think of ways that I could talk about astronomy, I wanted to do something different. So I thought that in my local, community that I know of, no one's doing this art plus science things. And I really loved her comics. Right. So I thought that I could, change it into comics. So it's not just a drawing; it would be a comic and something people would read. So that's why. So I got the idea. So you could say that she planted a seed. Her stories, her posts planted a seed for that.
That's awesome.
So actually, when the first time she followed me back on Instagram and she shared the story, I was like, "Wow!" I actually sent the screenshots to my few friends that she's following me. She's an astrophysicist and she's such a great personality. And wow,
she's also just a really nice person. Like we actually know each other from in person because we did the same degree. And so before the pandemic, I would often just go for coffee with her and her adorable toddler, and just like vent about everything. And she'd just be like, yep, it's going to be fine.
So that's one very supportive.
Yeah.
So coming to advices by good friends, what would be your advice that you would share with a prospective graduate?
I think it's really important not to compare yourself to other people. Obviously, this is difficult when you go through an entire education system, which is built on comparing you to other people through grades and things like that. And then once you get to the graduate level, there are all of these things you feel pressured to do, like publish as many papers as you can and go to all of these conferences. And then you can look at people's websites and they just look so impressive. And then you're like, oh no, I am not impressive. And so I think it's just really important not to compare yourself to other people, because that can just plant like a seed of like imposter syndrome in your mind. And like it can be quite detrimental to your productivity if you just end up feeling down about yourself all the time. So try not to do that.
Right. And would you think that in the age of social media, the cases of imposter syndrome have gone a little up because people most probably tend to share their achievements, and if you're in a science, you're going to follow people in science.
Yeah, I think so. And also, you can just scroll down. I mean, I really love the science Instagram community, but the other thing is that you can scroll down and see loads of people posting about their productivity, and then maybe you're not feeling that productive that day, and you're like, man, why am I such a failure? It's really important to like distance yourself from that. I actually deleted Instagram for like 6 months last year because I was just so sick of looking at other people's lives.
I can understand. A lot of people do choose that. I think it's a healthy measure to take a break, because if you're going to have it over there, you're going to continuously open it up. So just deleting it and for a small break is always helpful.
Exactly.
So I think we've had some amazing answers and amazing details about the interesting research that you do. And finally, we are at the last question. Though I wish I had more questions to ask. So that this conversation would keep going on, learning about galaxies and how do they die. So the last question that I want to ask you, Kate, is that if you could suggest one book or author of any genre to someone, what would it be and why?
I love this question. I'm going to recommend the same book that I recommend to literally everybody who I meet, which is a trilogy called His Dark Materials by Philip Pullman. It is my favorite book. I read it every single year. And the reason why it's my favorite book is for a few reasons. The characters are absolutely amazing. and the story is
Right.
incredible. And whether you're like an early teenager reading it or you're older, you'll get something different from it. What you'll probably all get is an incredible attachment to these characters. But I think importantly, one of the main messages from the trilogy is that it really teaches you to question authority, and to question whether the things that people in authority are actually doing is correct or not. And thinking about how that affects basically everybody else.
I did hear you said it's a trilogy. I couldn't get the name of the book probably.
It's called His Dark Materials.
Okay. Wow. So what kind of genre is this trilogy?
It's fantasy. So one of the cool things about this book is that like there's a talking bear. All of the people have their souls outside of their body in the form of an animal called a demon.
Wow.
Which is really cool, right?
That's actually cool. So right now I'm watching this series, which is called The Grimm. So they also it's kind of fantasy, and people do not have the souls outside their body, but there are these few people who have, who are creatures hidden in the form of humans. So there are various animals like rats and snakes.
That's interesting. I might check that
So
out.
it's actually very interesting. So if you're into fantasy and you want something to binge on, it's a good series.
Yeah, this is also available as a series. There's been 2 seasons of it now. So if people find reading difficult, it's also available as a TV series. And I think they did an incredible job with the adaptation. So it very closely follows the books.
Wow. So I guess I would check out the series first.
I watched it all in one weekend.
I hope I find that weekend very soon, that free amount of weekend.
Yeah.
So with that, Kate, we've come to the end of the interview. I had a very nice time. And before we get, before we end this, I have some questions for you. Just as a follow-up, a few questions that came to your mind. So one thing that I wanted to know was that when I read about galaxy mergers, I found out that two galaxies merging together can start, a star formation. So how can that lead to a galaxy dying?
So basically, when the star formation happens, almost all of the fuel for the stars formation is
Right.
used up in forming the stars. And so once that happens, there's no fuel anymore. So naturally, the next stage is just a galaxy becoming dead because it's not forming stars anymore. Sorry, I just have to plug in my laptop real
Sure,
quick.
sure.
But yeah, I hope that makes sense.
Yeah, that actually did. So the last thing that I want to ask you, Kate, is it possible that within the same galaxy, one part of it is dead, like it's not creating any stars, just one part, and the other part is like having the starburst moment?
Yeah, that can actually happen, I think. So with the galaxies I was studying during my master's, one cool thing was that we could actually resolve which part of the galaxy was post-starburst. So you could see a part of the galaxy that had recently had a starburst and then been quenched, but then the rest of the galaxy, that did not happen. So we can figure that out. And we don't really understand why that happens, but it could be due to a few things. So if the post-starburst bit is in the center and it looks like it's a merger, then it's probably a merger. But also you could have the situation of the galaxy accreting, that is basically just eating another smaller galaxy. And so there would be maybe like a starburst in that bit that maybe wouldn't like extend to the rest of the galaxy. And also galaxies can interact with each other but not merge. And this can also cause like deformities in the shape of the galaxy, but can also cause like quenching and star formation in certain parts, depending on like the orientations of the galaxies.
Wow. So thank you so much, Kate, for answering all these questions. And I had a lovely time.
Yeah, me too.
So
Thanks so much
before
for
we,
having me on.
well, my pleasure. Thank you so much for agreeing to spend your weekend with me over here. So before we go, I hope that everyone who's been watching with us throughout has enjoyed learning about galaxies as much as I have. And before we say bye to each other, Kate, is there something you want to say? to conclude?
Um, I think I'll echo one of my supervisors in a recent colloquium when she said that I think the world will be a little bit of a better place if we all just remember to be kinder to each other.
Wow. So that's a very excellent note, and I think I couldn't add anything better to that. So this is where we end our episode 4 of the podcast. Thank you everyone for joining me, and bye bye. Have a nice weekend.